Hello, welcome to my YouTube channel. This is Filipino explaining. A sample of a radioactive material contains 10 raised power 18 atoms. The half-life of the material is 2.000 days. Calculate A. The fraction remaining after 5 days. B. The activity of the sample after 5 days. Solution. Section A of the question, the fraction remaining after 5 days. We shall use the formula n is equals to n naught a half raised power n, where n is the number, in this case the number of atoms after disintegration. Then n naught is the original number of atoms, in this case original number of atoms. Then this small n is the number of half-lives. So from the question, the half-life is 2.000 days and the original number of atoms is 10 raised power 18 atoms. So we have to find n, the number of atoms after disintegration, and after we are done with that, we find the fraction. Now the fraction, are we there? So n, we have said that n, this small n, is the number of half-lives, and this n is given by the time period given, in this case after 5 days. So you can say after time t over the half-life, are we there? And we have 5 days. The half-life is 2.000 days, 2.000 days, and we have n as 2.5 half-lives. Are we there? Therefore n will be equals to 10 raised power 18 a half raised power 2.5. Are we there? Okay, this gives us 1.767766953 times 10 raised power 17 atoms. These are the atoms remaining. So the fraction remaining is equals to n over n naught. And what is our n? Our n is 1.767 7,66953 times 10 raised by 17 divided by 10 raised power 18. Remember, here is atoms, and we get the answer as 0.17677. In 4 significant figure, you can put it as 0.1768. 0.1768 for significant figures. Okay, that's the answer for section A of the question. Section B, the activity of the sample after 5 days. The activity of the sample after 5 days. Solution: R is equals to lambda n. R is the rate of activity, lambda is the decay constant, and n is the number of atoms. In this case, the number of atoms, or you can say the number of atoms after disintegration, or we can say the radioactive material remaining after disintegration. Are we there? So R is given by lambda n. We have n. We have n is here. We don't have R. We don't know the value of our decay constant, so we have two unknowns. Then therefore we cannot use this relation, this formula, since we have two unknowns. Are we there? So it will force us, or we have to first of all find the value of this lambda, the decay constant, so that we have one unknown, which is the activity of the sample, or the activity of the sample. Are we there? Therefore the half-life is equals to into over lambda. Converting the half-life into seconds. Remember, the half-life is 2.000 days, so we convert that into seconds, and here we have 2 times 24 times 60 times 60. Remember, 1 day consists 24 hours, so 2 days we multiply by 24. 2 times 24, we are converting 2 days into hours. Are we there? And then we convert it to minutes. Remember, 1 hour is equals to 60 minutes, so we multiply by 60 to get the minutes. After that, we convert in seconds. Remember, 1 minute is equal to 6 seconds. What about the whole of these minutes? So we multiply by 60. Are we there? And we get 172,800 seconds. And now we substitute this into this formula. 172,800 seconds equals to into over lambda. Multiply both sides by lambda, and get lambda is equals to into over 172,800 seconds. Are we there? Six 0.69314718 over 172,800 seconds, and we get lambda as 4.011 times 10 raised to power -6. This is the decay constant. Decay constant. And therefore R, which is given by lambda n, will be equal to 4.011 lambda times 10 raised to power -6. Then we multiply by n. What is n? Here is our n. 1.768 times 10 power, say, times 10 power 17. Let's put it in 4 significant figures. For 4 significant figures. And therefore we have our R as 7.092 times 10 raised to power 11, and the units are, and therefore this is the final answer. 7.092 times 10 raised to power 11 BQ. BQ is in full is Becquerel, named for Henry Becquerel, the discoverer of radioactivity, and this is the SI unit for the activity. Are we there? Remember, one Becquerel is equals to 1 BQ. In short, is equals to 1 decay per second. Is equals to 1 decay per second. And all the unit, the Curie is still in common use. Remember, 1 Curie is equals to 1 CI, this in short form, is equals to 3.7 times 10 raised to power 10 Becquerel. 1 Curie is equals to 3.7 times 10 raised to power 10 Becquerel. But the SI unit for activity is Becquerel. So up to that point, I do believe that we have learned something, or have reminded ourselves some things. To find the fraction, first of all, we find what's not given, provided we have a small n, the number of half-lives. We have the original number of atoms, like in our case we are dealing with atoms. We have the number of atoms after decay. If I give we are not given any one of these, we use the others to find it. After that, to find the fraction, we just divide the number of integrations the number of atoms after disintegration by the original number of atoms. Then to find the activity of a sample, we use this formula R is equals to lambda n, where lambda is the decay constant and n the number of atoms after disintegration. Are we there? I've also applied this. Since you have you have been given the half-life, and we want to use lambda in this, in the first formula, we apply this relation and we get the final answer. Thanks so much for watching. Till next time.